Okay, so we are now trying to draw the picture of ordinals. So like we know that the class of ordinals is a strictly well-ordered class. So let's try to like see them on the picture to try to understand the this class as a strictly well-ordered set. But before that, like I'm going to introduce some adjectives, okay, that I'm going to be using all the time from now on. An ordinal alpha is called a successor ordinal if alpha is, well, guess what, is the successor of, if it's the successor of some ordinal gamma. It is called a limit ordinal if it is not 0 and it is not a successor. Okay? Now, let's start, as I said, try to draw the picture of ordinals. We're going to start with the ordinal 0 because it's the empty set. It's the least ordinal that you can get. You can't get anything smaller than this because then empty set would have a member. And then comes the successor of 0, which we called 1. Why can't you find anything in between these? Because in general you can't squeeze a set strictly in between a set and its successor. What's the difference between a set and its successor? You add one more element, right? Which means that you can't literally just squeeze something in between. If you have a superset of some set which is not equal to that set and which is contained as a subset in the successor, then it has to be the successor itself. So we can't put anything in between. And then comes 2. I'm going to keep taking successors. And then comes 3 and dot, dot, dot. And I have omega, which exists by the axiom of infinity, as you remember from a couple of weeks ago, which is called, which is an ordinal itself, as we checked. And I can keep taking successors. Okay, this is the ordinal which contains all natural numbers, and omega. This is the ordinal which contains all natural numbers, and omega and successor of omega. Now, I will say and so on and put dot, 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 which means that I'm just going to keep taking successors. Here's the question: can I put something here? When you look at this picture, what do you see? Any ordinal, okay, we proved that an element of an ordinal is ordinal, and we define the less than relation as the membership relation. So any ordinal is the set of all previous ordinals. Okay? You construct any ordinal as a set of all previous ordinals. So if there's an ordinal over here, so let's put question mark. It's like, you know, in games like Super Mario, there is question mark, and when you hit it like with your head, it tells you something. So we're just gonna open this box in a second. But tell me the following: if there is an ordinal at all over there, what would it be as a set? It would be what? Just look at the picture. Any ordinal is the set of all previous ordinals. If there's an ordinal over here, it would be it would contain all natural numbers, omega, successor of omega, successor of omega, and all these guys. If there's an ordinal over here, it has to contain simply, it has to be the set of all ordinals before it. Here's the question, can you construct that? Well, obviously, with your previous mathematical training, you would simply say that you would create a sequence like this, A0, A1, A2, dot, 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 B0, B1, B2, dot, 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 and you would say that I'm taking the union of the images of these sequences. So this is that. It is true, this is a set. However, you cannot prove that this collection is a set without further axioms. We will need the last axiom of ZFC we haven't introduced in order to construct the question mark, okay? And that is called the axiom of replacement. Now, this is, of all the axioms of ZFC, this is conceptually the most difficult one to understand because, first of all, I'm going to write a lot of symbols on the board, and then I'm going to quantify over formulas, which already says that this is not a single theorem, and then you're going to wonder when I explain what this axiom does, you're going to wonder, like, why can't we simply prove this using axiom of separation? And I'm going to tell you that it is a theorem that you can't actually prove that. So the point is, this axiom will probably raise some questions. So we're going to spend some time talking about this. So we start with a formula with two free variables. Let xy be a formula in the language of set theory such that, no, that's that. Now assume the following. If for all x there is a unique y such that phi of xy holds, then for any set A, for any A, there exists B such that for all y in B, for all y, we have y in B if and only if there is x in A with phi of xy. It would be good if everyone knew this axiom at the end of the course, but unlike other axioms, I don't expect first-timers to know this off the top of their head, okay? Like, because as you can see, there's a lot going on here. So for your exam purposes, I'm not going to ask this one, okay? I can tell you that. But you should learn this. Like, when I explain what this axiom does intuitively, it would be clear, really clear. You should know what this does. You can ignore the formal statement that I'm about to write down. So that is the axiom written in English. Let's write this in the language of set theory. Okay, so for all x, there exists y for all y prime there's a typo in the notes that I'm going to fix later. Oh, no. Never mind. I think this is equivalent to that. But I'll write this version. This implies for all A, there exists B for all Y. Y in B if and only if there exists X in A such that phi of xy holds. Bless you. Now, let me grab my purple chalk. This part of this formal statement simply says for all x there is unique y with phi of xy holding, because actually let me do it this way. For all x there exists y phi of xy, and as I said, the statement denotes is also true, but let me write it this way. And this for all x, for all y prime. Yeah, this is better. So what this says is the following. Assume that for all x there is y such that this formula holds. So for every x I can find some y such that phi of xy holds. And not only that, this y is uniquely determined in the following sense. If for some x you can find y and y prime such that these two hold, then y is actually y prime. Okay? And I can actually drop this part. The other part comes from like properties of first order logic. The other direction is already true, but I need that. So this simply says that for every x there is a unique y satisfying this, and this says that there is at least one y. And what this says over here is the following. Pretend that I have such a formula. If I have such a formula, the following happens. For all sets A, I can find a set B such that any element of B is paired with some element of X so that phi of xy holds. For every element of B, I can find something in A such that phi of xy holds. Okay? And conversely, if I have some X in A, there's a corresponding Y in B. Okay? Now what this says is, let's talk about the intuitive interpretation of this.
It is like onto function, right?
Yes. Not onto, it's, I'm actually guaranteeing that this is also, oh no, yeah, it's like an onto function, yes. Well, let me rephrase that. What this says is the following. Pretend that I have a formula which behaves like a function. Behaving like a function means what? It takes any x to a unique y. Okay? So this part, for all x there's a unique y such that blah blah holds. This simply says that this formula behaves like a function, meaning that it takes any x and it kind of sends that x to a unique y. If you have a formula which behaves like a function, I'm going to call these class functions, don't worry, I'm going to give a name to these. The axiom of replacement says the following. Pick any set A any set, each of these guys have corresponding, each of these x's have corresponding y's, right? Corresponding elements to which they are matched with this formula. For each x, there's a corresponding y, a unique y. Let's do it this way. A, B, C, D, E, F. This is my A. Now to this A, there is a unique x such that phi of AX holds. To this B, there is a unique y such that phi BY holds. To this guy, there's a unique z such that phi CZ holds. The axiom of replacement says I can put those guys into a single set. There's a set which exactly consists of the corresponding elements to these guys. Okay? So if you think of this as defining a function, what axiom of replacement says is that the image of A under this function is a set. Okay? Obviously, this is not a function because what is a function? It's a relation which is well defined. It's a set of ordered pairs, blah, blah. This is a formula in the language of set theory. This is not a set. So this is not really a function. But you can think of this as if it defines a function. If you think of this as defining some function, the axiom of replacement simply says the image of any set under this function is a set. Okay? Now, hopefully I didn't mess up the formal statement. Even if I did, I don't care. Over there you have the English, you have the statement in English, and more importantly, over here I just explained to you what this is supposed to do, what this means. Okay? If you have a formula with two free variables that defines a function which takes every x to a unique y, for every x there is a unique y such that this holds, then if you think of this as defining a function on the class of all sets, the axiom of replacement says the image of any set is a set. For any set, you can find a corresponding B such that blah blah holds. Okay?
It's not necessarily one-to-one.
You mean one of the arrows?
No, I mean.
By the way, I think I only want this. Repeat your question again?
It's not one-to-one.
No, it need not be. It need not be one-to-one. And I don't want the other arrow. Yes. I think even if I put the other, okay, if I put the other arrow, it will be a different axiom. It's not going to be what I want, but I think, well, if I assume the other one, I think I can prove this one as well. Okay? Well, because that's actually stronger. Never mind. This is fine as is. Okay? Yeah. And from this one, you can prove the other one as well. Now, because I dropped one direction of this, here it is possible that there is more stuff in the set B which is not matched by something. So it's not now, you thought of this as onto functions, now I make sure that it may not be onto. There may be more stuff in B which are not matched by any elements in here. Okay? But that's fine because if this is a set, by axiom of separation, I can simply get rid of this part, which is not, which consists of elements not matched. So I can, like, from this guy, using the axiom of separation, I can simply construct this set. Okay?
But it says for all y, there exists an x.
No, it doesn't say that. I just changed the arrow, right? It says for all y, if y is in, oh. Yes. I changed the wrong arrow. You're right. This is fine. This is fine. This may be onto. Actually, I'm just going to put both arrows so that everything will be fine. You see, if I put this, yes, you're right. It simply says that for every, like, it's supposed to be onto. For every y in B, there's supposed to be something over here. But I also want the actual direction I want is the other direction. For everything in here, I want to just collect all the guys which are matched to these by this formula into a single set. So I actually need the other direction as well. Okay. Okay. If I consider just this part, then it is not necessarily onto. Because if I considered only this part, this simply says that if there exists some x in A, then the corresponding y is in B. But there may be more stuff in B if I just put this arrow. But let me put both arrows, so this is fine. What I was saying earlier is that if you only put this arrow, you can prove this version as well, okay? Using the other axioms, namely the axiom of separation. Questions about the meaning of this? Now, how are we going to use this to construct this ordinal? We're going to do the following. Consider the formula phi of xy which holds if, let's say, what I'm doing is the following. I'm creating a formula. I'm creating this for, I can write this in the language of set theory if you want. I don't want to. I'm saying this. This is going to hold if the following happens. If x is not an element of omega, then y should be the empty set. So I am mapping any set which is not a natural number to the empty set. That's fine. I can do that. And I'm mapping some natural number to the ordinal s of omega x times. So I'm sending any natural number to the ordinal obtained by taking the successor of omega x times. Okay? Now I can write this more properly if you want. I can say that to the limit I'm sending x, I mean this holds if x is a natural number and y is in the ordinal which contains x many limit ordinals, okay? I can say something like this and it will properly define this, but I don't want to go into that detail. I don't want to go into details. As long as you understand the intuitive definition of this, it's fine. Now everybody understood what I did over here. I'm sending in a natural number to this ordinal. For example, 0 will be mapped to omega. I'm taking the successor 0 times. I'm taking the successor of omega 0 times. I'm sending 1 to s of omega. I'm sending 2 to s of omega, and so on. I'm sending all the other sets to the empty set. Now, by the axiom of replacement, the image, okay, I'm going to put this in air quotes because I haven't defined what this means. The image of omega under phi is It is which set? It is this set. Is a set. So it is this set. So this collection, it's a set. Now I'm going to take the union of this. Let me call this U. Then union of U, okay, I'm going to call this W. Then union of W is an ordinal. Indeed is the second limit ordinal. This question mark is the union of W. Okay? So I can construct this as follows. I look at, now I'm going to use terminology I haven't defined. I'm going to talk about these in a second. I look at the class function defined by this formula. It sends every non-natural number to empty set. It sends natural numbers to these guys. I look at the image of natural numbers under this. What do I mean by this? I simply want to look at this set. By axiom of replacement, this collection is a set. Now I take the union of this. The union consists of all the stuff over here. And it consists of exactly all the stuff over here. So it is the ordinal I was looking for. If you haven't understood it, I can do it with a Jedi mind trick. Like, this is the ordinal you're looking for. Questions? Now, the point of introducing the axiom of replacement was simply, at least at that point, was this. Intuitively speaking, it is like if I send 0 to this, 1 to this, I want this collection, it's supposed to be a set. Just look at it, come on, this is supposed to be a set. But without this, we cannot prove that this is a set. Okay, so we introduce this axiom and it becomes a set. There are variations of this, like as I said, if you erase one of the arrows, did I erase the correct arrow now? Yes, this should be fine. From this, you can prove the stronger version as well, okay? And there are other variations which I'm going to talk about in a second. You can put parameters around. For example, pretend that over here I had a third set Z. And somehow I involved this Z in the definition. I said something like this happens and Z is blah blah. That is still true. So you can put parameters in this phi, okay? And those versions are provable from this version plus the other axioms. That's not actually completely trivial. I had to look it up online to see that whether that was actually true. Because sometimes if you don't put enough axioms, you can't prove that like stronger versions of these are provable from the weaker versions and so on. And let's see. Now, we will be using the axiom of replacement in future. This is important. Indeed, even though I told you like you don't have to know this off the top of your head, at least if you're a first timer, you should simply understand what it does. That's true, you should understand what it does, but let me tell you the following. The real power of ZFC comes from this axiom. This is like, in practice, you may get away with not using this for some parts of mathematics, but this is, if you're doing set theory, this is really important. This is where the real power of ZFC axioms comes from. Now, I'm going to introduce some terminology to talk about such formulas, because I don't want to say every time, look at the formula for which, for all x, there is a unique y. So I'm just going to define certain words to mean certain things about such formulas. But before that, let's understand one more thing about the axiom of replacement. As you can see, this is not a single axiom. This is like axiom of separation. I started with a formula in the language of set theory. How many formulas are there in the language of set theory with two free variables? Infinitely many. Indeed, countably infinitely many. This is not a single axiom. This is an axiom scheme. So it consists of infinitely many axioms. For every formula you can write down, I am declaring this to be an axiom. So there are actually infinitely many axioms introduced over here. Okay? Is that understood? Now, let's introduce the terminology I talked about. Yes?
There should be y equals that, right?
Where?
X is in W, y has to be equal.
Oh, yes. Yes. Thank you for that. Otherwise, it wouldn't make sense, right? This holds if when x is in omega, this should happen. If x is not in omega, this should happen. Yes. Yes, you're right. How did I forget that? Anyway. Now, let xy be a formula such that for all x there is unique y with 5xy. So let's say that x, for every x there's a unique y such that this holds. Then we shall say that this guy, which, as I said, we can think of this phi as defining a function, right? It takes some x to some unique set y. It's not really a function in the technical sense of the word function. Is everyone aware of that, right? Is everyone aware of that? A function is a set of ordered pairs such that blah blah happens. Over here, when I use the word function, I mean your previous intuitive understanding of the function. It takes a single input and produces a unique output. So we should say that this guy defines the class function f sub phi. And write f sub phi of x to denote the unique set y with phi of xy. So from now on, when I have such a formula, I'm simply going to write f sub phi of x to denote this unique y, just to save some time, okay? And because I'm like thinking of this as some function, not a function in the technical sense, but in the intuitive sense, I'm just going to use the function notation. We shall also use the available notations for functions for this f sub phi as follows. So I'm going to write f sub phi of A to denote the set of all y such that there exists x in A, blah, 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 phi of xy holds. Okay? And I am going to use the restriction symbol as well. So when I restrict this to some set A, I'm basically looking at a set of all such guys. Now, let me restate axiom of replacement with this notation. Let f sub phi be a class function. What this says is, what does this say? There is a formula such that for every x there is a unique y, blah blah, exactly what we did. If you have a, here's axiom of replacement written in a compact way. If you have a class function for any set A, the image of the set under this class function is a set. Okay? This is exactly f sub phi of A, if you put both the arrows, obviously. Otherwise, this is going to be a subset. Like if you just drop this part, it's going to be a subset of, it's going to be a subset of whatever you have here. But like in this form, the axiom of replacement simply says that for any, if you have a class function, the image of any set is the set itself. Okay? So from now on, when I can write down a formula that defines some class function, like I'm going to say that I'm sending these sets to these sets, and I'm going to send these sets to these sets. If my rule happens to assign a set, uniquely assign a set y to every set x, then when you look at the image of any set under my rule, it's going to be a set. Okay? Is this understood about axiom of replacement? Now, if this is too complicated or too abstract, you can ignore this formal statement, even that statement which I wrote first. You can forget these, but you should not forget this. You should not forget the meaning of axiom of replacement. The meaning means that take a class function, take a set, the image of that set under that class function is a set, okay? Questions? Now, in future, when I use such a notation, you are not going to think that this is an actual function, right? This is not an actual set of ordered pairs. This is not a set. This simply denotes that there is a formula around which uniquely assigns a set y to each set x. And because it behaves like a function, I'm just using the usual function notation for it. Okay? Because writing things formally in the language of first order logic, it's just cumbersome and difficult, and as you can see, I sometimes make mistakes by putting wrong arrows around, okay? So this is better, this is more intuitive. Now, let me prove one last thing, which I should have proven earlier, but I completely forgot because this was more important. Let me prove that finite ordinals are actually natural numbers. Okay? Every natural number is a finite ordinal because we proved that every natural number is finite by definition, and we proved that every natural number is an ordinal. Let's prove the other direction as well. It is an easy proof. If alpha is a finite ordinal, then it is actually a natural number. Okay? So on the picture I just erased, the stuff up to omega is exactly the set of finite ordinals. So the first infinite ordinal is omega. Okay? Without this, I can't really say that the first infinite ordinal is omega, because that picture is no proof that, like, I know that, never mind. I mean, on the picture it's clear that omega is the first infinite ordinal, but how would you argue that really? You can't refer to that picture. So let alpha be a finite ordinal. assume that this fails. Then, given two ordinals, if given two ordinals alpha and omega, if alpha is not a member of omega, what can you tell me? Then either they're the same or this is a member of alpha, because any two ordinals are comparable with respect to the membership relation. Okay? In both cases, we have that this is a subset of omega, because if alpha is omega, then omega is a subset of alpha. If omega is a member of alpha, well, alpha is transitive. Any of its members is actually a subset. So in this case, the transitivity of alpha implies that this is also true. Now, if alpha were finite, oh no, sorry. Since alpha is finite, there is an injection, there's a bijection f from alpha to n for some natural number n. But then, well, this guy, as far as I can see, contains all natural numbers, which means that I can restrict this function to successor of n. But because this is a bijection, this would be an injection. Well, having an injection from n plus 1 to n seems pretty contradictory to me. It contradicts what? Why can't you find an injection from a bigger natural number to a smaller natural number? By the pigeonhole principle. Good. Contradicting the pigeonhole principle. Pigeonhole principle. Thus, alpha is, our assumption is wrong, so alpha is actually an omega. Okay? So omega is the set of all finite ordinals. So let's see. 0, 1, 2, 3, dot, dot, dot. These are my finite ordinals. Here is the first infinite ordinal, omega, s of omega, s of omega. This is the first limit ordinal, dot, dot, dot. This is the second limit ordinal. Now, for reasons I'm not going to explain at the moment, I'm going to show this by omega plus omega. Omega plus omega is exactly the ordinal I constructed over there. This is the second limit ordinal. Now, you can guess what I'm going to do. I can use the axiom of replacement to iterate this process. I'm going to take the successor of this and successor of that, and I'm going to put dot, dot, dot over here to denote that I just keep taking successors. I will claim that there is an ordinal over here. Why? By axiom of replacement. Send 0 to this, 1 to this, 2 to this. Look at that class function. Look at the image of that class function. Take the union. There is some ordinal here, which is denoted by omega plus omega plus omega. Okay? And I can keep doing this. Now, by axiom of replacement, I can just iterate this process over and over again. Until where? Well, there is no end. But if you try to take this approach from bottom to top, all the things you can consider, all the things you can construct are going to be countable. You can check that all these sets are countable. There's another approach where you, like, with this approach, with this bottom-top approach, you can't construct uncountable ordinals, like infinitely many steps. you're gonna just keep applying the axiom of replacement, but all these are gonna be countable. Are there uncountable ordinals at all? Maybe there are none. Next lecture, we're gonna prove that uncountable ordinals exist. We're gonna talk about the Hartog's number of a set, and we're gonna prove that ordinals represent exactly Waller sets, which was the original motivation for introducing ordinals. What else are we going to do? Yeah, I need to take a look at the syllabus because I change the order of topics sometimes. Anyway, I'll see you next week, Tuesday.